sklearn, model selection, stratified shuffle split. Description: stratified shuffle split is a cross-validation strategy that ensures that the proportion of each class in the data is preserved in both the training and testing sets. This is crucial for classification tasks, where maintaining class balance is essential for model performance. Inputs: N splits the number of reshuffling and splitting iterations. This determines how many different train test splits are generated for cross-validation. Test size: the proportion of the data that will be allocated to the test set in each iteration. It can be a float between 0 and 1, a number representing the absolute number of test samples, or none, in which case the value will be set to the complement of the train size. Train size: the proportion of the data that will be allocated to the training set in each iteration. It can be a float between 0 and 1, a number representing the absolute number of training samples, or none, in which case the value will be set to the complement of the test size. Random state controls the shuffling applied to the data before applying the split. Pass an int for reproducible output across multiple function calls. Outputs: train index: a generator that yields indices for the training data in each iteration. Each iteration produces a pair of arrays, one for the training indices and one for the testing indices. Test index: a generator that yields indices for the testing data in each iteration. Each iteration produces a pair of arrays, one for the training indices and one for the testing indices. Steps: the data is first shuffled to ensure that the split is random and unbiased. The shuffled data is then split into training and testing sets, while maintaining the proportion of each class in the original data. This ensures that the model is trained and tested on data that reflects the true distribution of classes in the dataset. Metrics: accuracy measures the proportion of correctly classified instances. Precision measures the proportion of correctly predicted positive instances out of all instances predicted as positive. Recall measures the proportion of correctly predicted positive instances out of all actual positive instances. F1 score: the harmonic mean of precision and recall, providing a balanced measure of both metrics. Visualization plots: confusion matrix visualizes the performance of the model by showing the number of true positives, true negatives, false positives, and false negatives. ROC curve plots the true positive rate against the false positive rate for different classification thresholds, providing a visual representation of the model's ability to distinguish between classes. Precision recall curve plots the precision against the recall for different classification thresholds, highlighting the trade-off between these metrics. Fine-tune parameters: test size: adjust the proportion of data allocated for testing to optimize the model's performance. On unseen data, N splits: experiment with different numbers of splits to ensure adequate coverage of the data and stability of the cross-validation results. Uncertainty methods: confidence intervals estimate the range of possible values for the performance metrics, providing a measure of uncertainty in the results. Bootstrap aggregation: resample the data multiple times to generate different models, and use the distribution of their performance to estimate the uncertainty. Challenges and fixes: challenge 1: class imbalance when some classes are significantly underrepresented. Stratified shuffle split may not be able to preserve their proportions effectively in the split, leading to biased model training and evaluation. Sample use case: a dataset with 90 instances belonging to class A and 10 instances belonging to class B. Stratified shuffle split might still create splits where the training set contains a disproportionate number of instances from class A. leading to a model that performs poorly on class B. Fixes oversampling minority classes, undersampling majority classes, or using weighted loss functions during training to mitigate class imbalance. Challenge 2. Data leakage if the data is not properly shuffled before splitting. Information from the test set might unintentionally leak into the training set, resulting in artificially inflated model performance. Sample use case: a dataset with time-dependent features, where splitting the data chronologically might lead to information from the future test set being included in the training set. Fixes ensure that the data is shuffled thoroughly before splitting, especially when dealing with time-dependent features or datasets with sequential patterns.